Hi, this is Michelle Cullen with Astronomy 103A, and week 4 I'd like to do a mini lecture on radio telescopes. We're going to be covering Learning Objective 7, which is covering what can modern radio telescopes discover about the universe. Well, it turns out a lot. The largest dish telescopes are taking pictures of the naturally occurring radio waves that are being emitted in space by many objects, such as, well, stars, planets, even the Sun and Jupiter broadcast in natural radio waves. So do galaxies, especially perhaps super giant black holes in the center of galaxies, pulsars, quasars, masars. These are all emitting natural radio light. Yes, radio is a form of light that we're going to be learning about next week, and you may have already touched upon this week. So remember, radio light can travel through dust in space, making hidden galaxies and forming solar systems visible. So it makes this a very powerful tool. Here's an example of two different pictures of the same galaxy, M87, one in optical and one in radio, where the radio waves have been converted into a visual light image that we can look at. What we're seeing here is the center of the galaxy and a possible black hole with the energy jets. So a lot more information is available by using radio telescopes than regular optical. Here's a model of an active galaxy that is Hercules A and the comparison between visible and radio. So here we have it, a model, and this is from the Hubble Space Telescope YouTube channel. So this is what it looks like invisible. So you can see there was a lot more that we could see by using radio. This is what we see with a radio telescope. These jets that are of energy that are being shot out from the center of a galaxy that are invisible to visible light. Here is another view from a radio telescope converted into a visual image of the cosmic microwave background radiation. It's a very faint, ever-persistent radiation everywhere we look in the universe. It was discovered in the 1940s by the Nobel Prize winning discoverers, American astronomer Arno Penzias and Robert Wilson. So what they're showing here is that this all-sky picture of the universe showing what it looked like at deep time, deep space, 13.7 billion years ago. And we're looking at these different colors are temperature fluctuations. And they're corresponding to these little seeds of energy and packets of matter that grew into becoming galaxies. So this is a pretty cool use of radio telescopes. We've got radio telescopes all over the world, well, especially for NASA, in 3 places specifically that track the deep space. And these 3 ones, the Madrid, Goldstone, and Canberra, look from the North Pole image, can track all of space and all of our probes that are sent out within the solar system, as long as they're about 10 times further away than the geocentric orbit here. Then once they get to be 30 kilometers away, we can look at all of the different space probes that are being sent away from Earth to different planets and moons and comets and very far away. So this is how we use radio telescopes to track space probes. So how do radio telescopes work? Well, radio telescopes work on radio waves, which are the lowest and longest frequency of radiation in the electromagnetic spectrum. So these waves can have a different an amplitude and a wavelength. That the wavelength can be as large as a planet, and then as it gets smaller and smaller, larger than a building, larger than a football, 300 football fields, down to 30 meters. 3 meters, we're still in the broadcasting radio that we're used to listening to on FM. So this is how they work by having a giant antenna, which has to be pretty much as large as whatever wave they're looking at, and it reflects in the dish to the focus point where scientists can use instruments to convert the radio waves into useful data for them. So you can listen to the radio as sound, or you can print it onto a computer screen as digital bits and bytes. Now, I mentioned that the radio waves can be very, very large. They could be as large as the state of Alaska. So if you were to get a telescope that big, it would be impossible to build, but you can use the concept of interferometry to build an array of telescopes, which each individual telescope is not that large, but together they can span this giant field, or they can span between countries, and they can gather very, very large radio waves and take those into account to analyze them. Another good thing about radio waves is that they come through the atmosphere. They're not being filtered out by the atmosphere like a lot of visible light and other types of energy you're going to learn about. So you can have radio telescopes looking for radio waves on sunny days and in the middle of cities, or even on cloudy days. It doesn't depend on the weather. What it does depend on is radio pollution, which can be other communication radio frequencies that are being broadcast, and those can get in the way of these scientists trying to gather information from space. So we have international quiet zones and different frequencies that astronomers have protected so that they can use those frequencies to gather information. From Australia to Chile, Puerto Rico to Russia, there are radio telescopes all over the world, North and South Hemisphere, trying to do research on using radio waves. The largest, newest one is called FAST, F-A-S-T, and that stands for 500-meter something telescope that's in China, and it just was finished in July of 2016 and is supposed to be operational anytime now in 2016. Here's a scene from the movie Contact, based on Carl Sagan's wonderful book about discovering an extraterrestrial life. She's listening to the radio telescope. Instead of noise, she's hearing a rhythmic frequency.
Right ascension, 18 hours, 36 minutes, 56.2 seconds. Declination plus 36 degrees, 46 minutes. 56.2 seconds.
Soullessness, that's only people.
Confirmed! Right ascension, 18 hours, 36 minutes, 56.2 seconds. Hey, is anybody awake in there? I'm moving the array. Confirmed!
Spot does a bogey.
Right ascension, 18 hours, 36 minutes, 56.2 seconds. Declination.
We're on it.
Plus 36 hours, 47 minutes, and 1 second. Strong possible pulse chain. Submarine force. I'm moving the rest of them now, and I need you to confirm the coordinates.
Check the status of the array. It's doing all the dishes. All systems nominal. Hello. I need a full systems check.
Coordinates confirmed. Willie's checking the system now. Stay on top of the system, diagnostics. Check the reference point offsets, and I want you off axis on 27 the second we get there. And tell Willie to break out the big boy.
Copy that. Willie,
So if you haven't watched the movie Contact with Jodie Foster, you really should. It's a very exciting movie, and it has to do with a lot of radio telescopes. So I hope you've learned a little bit about radio telescopes, from all the things they can do, how they help us discover the universe, ranging from all of the things, from looking at the sun to the center of galaxies, peering through dust that's not visible with the visible light, to tracking our space probes and even searching for life out there that might be broadcasting radio waves for us to hear. It's a really interesting concept that we've been broadcasting for less than 100 years, and so you think anything within that range of speed of light that radio waves would travel, any life out there might be able to hear us. There was a recent discovery, well, proclaimed SETI signal from Russia in 2015 that they said they found a very strong signal. Later this year they said that it was probably just a spy satellite, and since they weren't able to duplicate it when they looked back in the same region of the universe, and they could not repeat it. So it's exciting. Maybe in our lifetime we'll actually use radio telescopes in a big way to figure out more about life. Hope you've enjoyed this. This is Michelle Cullen signing out.